process is labor-intensive, time-consuming, error-prone, and dangerous. The quality of the inspection result is not particularly high. That's why people already try to use drone to help inspecting a bridge. That idea is not a new idea, so a lot of people are trying to do that. But the current practice still involves a large number of manual steps, which our BIT system aims to automate away. So that's the new thing, that we want to automate these previously manual steps. So what are these steps? When you are given a target bridge segment to be inspected, let's say you want to inspect a particular bridge segment, you need to first create a 3D model for it so that you can compute the inspection flight path for a drone and you can present the final inspection result. So you need a 3D model. And then you are going to compute that flight path for inspection. And that flight path better covers all the what we call inspection elements on the bridge. By inspection element, we mean important areas on the bridge that are significant from the standpoint of inspection check. Like you have to cover those points. That's called inspection element. And then you need to fly this drone along this path autonomously without human intervention, even in areas where the GPS signal is not available. That's the big if, right? When the GPS signal is not available, the drone is still able to fly autonomously. And finally, from time to time, the drone has to stop at these inspection elements and take high quality picture of these inspection elements. And finally, you need to analyze the images captured by the drone to identify defects and classify them into their corresponding categories. Right? So that's the things that you need to do. So all these steps currently are mostly done manually, and we want to automate them away. So that's what we want to do. So how do we create a 3D model? Given a target bridge segment that you want to inspect, first we take a set of pictures at that bridge segment at a well-defined angle and well-defined distance to create something we call a rough 3D model. And then that's where magic comes in. Based on this rough 3D model, we use this rough 3D model as a baseline and continuously scan the bridge segment and apply the so-called structure from motion algorithm to create the detailed 3D model that we want. Once we have this detailed 3D model as shown here, we can use it for interactive browsing and for computing the inspection flight path. So how do we calculate this path? Given a target bridge segment and its detailed 3D model that I just described, we first select a large number of waypoint candidates surrounding the target bridge segment. And for each waypoint candidate, we apply a so-called visibility calculation algorithm that computes the coverage of the bridge from the standpoint of that waypoint candidate. And then based on this visibility calculation result, we filter and select a subset of this waypoint candidate to form the final inspection flight path. Now, the resulting inspection flight path has the following property, that waypoints on this path are guaranteed to cover each and every inspection element, which again, important areas of the target bridge that we need to inspect. It can cover each and every inspection element at least a certain number of times. So it guarantees to cover all the important inspection elements. This is something that existing drone-based bridge inspection system cannot do. Right? So now we have this inspection flight path that I just calculated. We just need to fly the drone along the path. Nowadays, this is not an issue. This is not a problem anymore. There are a lot of systems can fly a drone autonomously without human intervention along a predefined path. But we need to do this until even when the drone is flying under the bridge, where the GPS signal is not available. So why is this important? When a drone flies, it needs a positioning information of itself, which is typically provided by the GPS signal. So when a GPS signal is not available, it doesn't have this position information anymore, and therefore it cannot fly properly. To address this problem, we use a so-called visual SLAM algorithm that can compute dynamically the drone's position and therefore enable the drone to fly under the bridge even when the GPS signal is not available, right? So how does this visual SLAM algorithm work? It's shown on the left. So when a drone flies under the bridge, its camera is facing upwards, so it's seeing something upwards, and returns a continuous sequence of images. This visual SLAM algorithm is going to analyze this sequence of images and compute the drone's position by capturing the similar points on consecutive video frame, and then you can calculate the drone's position. The same visual SLAM algorithm can also enable a drone to fly in an indoor environment where, by definition, the GPS signal is not available, as shown on the right. So it can now fly smoothly and based on the planned path without any problems. So the next step, now we can fly the drone along the path. But we want the drone to fly in the following way. We want the drone to fly faster. So they won't look at everything very carefully, but it's very slow. We want it to fly faster when there's nothing going on. And we want it to slow down and pay attention when there's something going on. So that means that the drone needs to have a capability to feel that there's some sign of trouble or some sign of defect as it flies along the path, as shown on the left. Like usually it just flies at a high speed, and then from time to time it will stop and take a look at it if there's something interesting. And after that, it picks up the speed and move on. That's the desirable behavior that we want. All right. Now, when the drone flies along the path and it reaches an inspection element, so remember I say inspection element is the part of the bridge that's important from an inspection check point of view. In this case, the screw area on the frame of the bridge is an inspection element. That's something we care. This is another example. This is so-called support pad on the pier of the bridge. This is also an inspection element. As the drone flies, encounters such inspection element, it just stops and carefully takes a picture at them by taking picture from a proper distance, at a proper angle, and with the right focus. Therefore, the quality of the resulting picture can meet the formal inspection requirement. So you need to make sure the quality of the picture is high enough to meet this formal inspection requirement. And the last step is that once you get all these images from the drone, BITS uses AI algorithm. This is what AI is good at, to analyze things. So BITS just use a pretty standard sort of DNN-based AI algorithms to analyze images coming from the drone and detect possible defects, classify them into their corresponding categories, puts together the analysis result, and generate the inspection report. So once BITS can automate all of the above steps, the rest is very easy. That all a bridge inspection operator needs to do now is to specify the bridge segment that he intends to perform an inspection check on, like on the left, and gets the process rolling, and the BITS system will take care of the rest. He can actually monitor the progress of the BITS system a little bit if he chooses to, but he can do this from his desktop or laptop computer by viewing the real-time video feed coming from the drone and shown in the right. So that's what you are going to see, how the BITS system is doing. So what's the upshot? The upshot is that BITS uses this end-to-end automation capability to cut down the bridge inspection cost by half and reduce the elapsed time to 1/3. The degree of automation of existing drone-based bridge inspection system can be classified into 4 levels, if you wish. So level 1, zero automation. Everything is done manually. That's almost like today. Most, if not all of the drone-based inspection systems work like this. Level 2 automates the steps of computing the inspection flight paths and flying drone along the path. So it automates these two tasks. Level 3 is level 2 plus the automation of taking high-quality pictures of the inspection element so that the resulting picture's quality meet formal requirement. Level 4 is the level 3 plus the automation of analyzing these captured images and generation of the inspection report. So it used to be the case that a bridge inspection operator needs to be intimately involved in the monitoring and control of a drone-based bridge inspection process. The guy is very nervous whether there's something going on and whether everything is works just right. So he has to stare at the screen all the time. So that's what's happening there. All right. But with bits correspond to level 4 automation. We automate almost everything. All right. This is no longer the case. The same guy, the same operator, just needs to specify the bridge segment to be inspected and hit the start button, and then he can sit back, sip his coffee, and wait for the result to come back. Now the gap between these two operating modes reflect the enormous productivity gain enabled by the end-to-end automation capability of the bid system. So that's why it's so interesting. Right? Finally, I'm going to talk about a system called COTA, which is designed to automate the stress testing and the stress testing of an ADAS system and its subsequent enhancement based on the test system. I'll explain why.